Hello and welcome to Bedroom Physics. Today I'm going to be talking about single-dimensional motion, and I'm going to start off with derivatives or rise over run. If you haven't taken calculus yet, that's okay. At my school you can take Physics 1 without having finished Calculus 1, but as Richard Feynman has said before, you had better learned it. It is the language God talks. In any case, let's get started. What is a derivative? Well, let's start off with a change in distance, okay? So say we have a vector and it's going from point A to point B, and this would be a displacement, right? Point B minus point A. Now, for our purposes, we're going to say that point B and point A represent distances. So if we were to follow this vector, we'd have a displacement of distance. But in our universe, we don't just travel through distance, we also travel through time. So not only is this a change in distance, but it's also a change in time, as you can see here. If we were to graph this change in distance over time, we'd have a graph that looks something like this. Notice how the path of the graph is not the path that we take in real life. Say I were to move straight ahead of me in a straight line with an increasing amount of speed. My path would be straight, but the graph that would represent my path would be something like this, would be a curve. And as you can see, our y-axis is the change in distance, or distance, and our x-axis is the change in time. If we wanted to calculate how fast the distance was changing over time, this would be known as the rate of change, which is rise over run. In this case, our rise is distance and our run is time. So our rate of change would be the change in distance over the change in time, or you could say the final distance minus the initial distance over the final time minus the initial time. This would give us velocity. In this case, it'd be velocity average. As we know, velocity is represented by meters over seconds, or distance over time. Again, this is the average velocity. If we wanted to find the velocity at any given time at a single point, or at instantaneous velocity, then we'd have to take a derivative. The way that we find a derivative is by taking the limit of the change in distance over the change in time as the change in time goes to 0, which is noted by dd over dt, which is equal to the instantaneous velocity. Now, if you don't know what a limit is, in other words, this just means that we're taking the change in distance over an infinitely small change in time. Not a non-existent change in time, but an infinitely small change in time. So the limit is going to 0, but it's not at 0. Likewise, we could find the acceleration, which is a change in velocity over time. So, change in velocity over change in time, velocity final minus velocity initial over time final minus time initial is equal to acceleration average. If we wanted to find the acceleration at any given point, or a point infinitely small, we'd have to take the limit. So we'd have the limit of the change in velocity over the change in time as change in time gets infinitely close to 0 or goes to 0, which is also noted as dv over dt, which is equal to the instantaneous acceleration. Now that we know all this information, let's extract some of it and put it in our toolbox. So we know that the average acceleration is the final velocity minus the initial velocity over time final minus time initial, change in v over change in t. We know that our velocity average is equal to distance final minus distance initial over time final minus time initial. But we also know that when we want to find an average, the way that we do it is all of our data values added up over the amount of data points that we have. In this case, we have two data points, v initial and v final, so we'd put them over 2. So this v average is equal to change in distance over change in time, and it's equal to v initial plus v final over 2. And this we'll get to in a moment. The goal of all these formulas is to find the final distance. But let's start out with acceleration, velocity, and time. If we were to rearrange this formula in order to find the final, we couldn't, because it doesn't involve the final. The closest thing to final distance that we have is a final velocity. So let's just solve for that first. What we're going to do in order to get v final is multiply over a change in time and add a velocity initial. And we'll have change in time times acceleration average plus velocity initial, which is equal to v final. But we could also derive another formula from this. We could find t, or the change in t. In this case, change in t would involve subtracting the velocity initial to the right side and dividing it by acceleration average. So we're going to get change in t is equal to v final minus v initial over acceleration average. So let's add that to our toolbox. Moving on, we want distance final, and we used up our resources for this acceleration formula. Let's move on to our velocity formula. So we know that velocity average is a change in distance over a change in time, but we also know that it's equal to velocity initial plus velocity final over 2. So if we wanted to find d final, we could set change in distance over change in time equal to velocity initial plus velocity final over 2. And we could solve for distance final, right? In order to do that, we have to multiply the change in time by the formula on our right side here and add the initial distance, and we're going to get a change in time times v initial plus v final times a half plus initial distance, and it's going to give us distance final. But wait a second, we just solved for the change in time. We have a formula for it, right? Change in time is equal to velocity final minus velocity initial over acceleration average. So why don't we just plug in this formula to this second formula and see if we can get something out of it. If we multiply v final minus v initial over acceleration average by v initial plus v final times a half, we're going to get v final squared minus v initial squared over our acceleration average times the half, or the denominator times 2, and our distance initial and distance final is retained. Notice how in each one of these formulas something is missing. The first formula, there's no distance. The second formula, there's no acceleration. In the third formula, there's no time. And this helps us when we're missing some of these elements. But say we wanted a formula which involves time, acceleration, and distance. Well, there's one last formula that we have, but it's a little long to do verbally, so I've written it down. So this derivation starts with a velocity average, which is equal to 1/2 times v initial plus v final. But we know what v final is, right? We know that v final is equal to change in t times average acceleration plus velocity initial. So why don't we just plug in for v final? And we're going to have 1/2 times v initial from the original formula, and when we replace v final, we're going to have plus v initial plus change in time times acceleration average. And as my differentials professors used to say, when you mix yellow and red, you get white. So this is going to be equal to 1/2 times 2 times v initial plus change in time times acceleration average. But we know that velocity average is not just equal to v initial plus v final over 2. It's also equal to a change in distance over a change in time. So let's set the formula that we just derived by the change in distance over time. After all, we are looking for distance final. And it is here. All we have to do is multiply over change in time and then add the initial, and we're going to get 1/2 times change in time squared times acceleration average plus change in time times velocity initial plus distance initial, which is going to be equal to distance final. The last thing that I want to say about this concept is note that I haven't specified any direction. For my directions, I've written D, and all my subscripts are non-directional. But it is important to remember that in physics, we have 3 reference directions. We calculate motion in the x-axis, we calculate motion in the y-axis, and we calculate motion in the z-axis. You cannot mix up the formulas with x's and y's and z's. If you're looking for a v final in the x direction, then all your terms have to be in terms of x. If you're trying to solve for the final distance in the x direction, all of these terms have to be in terms of x, along with all the other formulas. That is not to say that we can only use these formulas for motion in the x direction. In fact, we can use these formulas in motion in any direction, x, y, z direction, but you can't mix them up. Your answer will be nonsensical. In any case, this has been the single-dimensional motion concept. I'll see you in the example video.